Dear participants, welcome to the second session of Day 4 Room 1 presentations. In this session, we are hosting Professor HAYET Chihi from the Center of Water Research and Technologies, CERTE, and the Ministry of Higher Education and Scientific Research, Tunis, Tunisia. Professor Dr. UMUT TÜRKER and Dr. AKEEM OLADIPO from the Civil Engineering Department of Eastern Mediterranean University, North Cyprus. Welcome, professors, and thank you for joining this session. Firstly, I would like to invite Professor TÜRKER from the Eastern Mediterranean University to deliver his presentation.
Thank you, Mustafa.
Welcome, Professor.
Thank you. Before I start my speech, I would like to thank Professor HÜSEYIN GÖKÇEKUŞ and his team for organizing such a nice organization as usual. We get used to it from Hüseyin Hoca. Thank you again. Well, today I will discuss the role of increasing riverbank vegetation on flow dynamics. As we know, either in natural or artificial channels, vegetation is always interfering the flow. Somehow, some way, they find a way to be present there, and their aim is always to change the morphology, change the system. Well, independent of the stiffness of the vegetation, which I mean whether they are flexible or rigid, or depending on their heights, whether they are submerged in the water or they are emergent from the water, or their distribution, such as linearly distributed or staggered distribution, it is very well known that they play with the dynamics of the flow. How? Well, they change the direction of the flow, they change the velocity of the flow, and they change the behavior of the flow. And all these, of course, modifies the morphology of the channel. Thus, in environmental hydraulics, the effect of vegetation on the channel bed and bank is an important engineering problem that should be clearly analyzed and understood for the precautions that we need to take. Well, the sketch of velocity profile in the flow direction is a boundary layer flow, submerged canopy flow, and emergent canopy flow is shown in our figure. And what we see here is that the existence of vegetation is clearly showing that they have the ability to minimize the effect of the eddies, meanwhile minimize the velocity profile that occurs in the channel. Well, in A, it is in boundary layer flow. In our figure, we can easily see that depending on the speed of the velocity profile, the eddies are generated at the bottom of the bed of the flows, and these eddies, of course, depending on their effects, might create erosion or similar activities at the bed and the sides of the channels. On the other hand, when we have a channel filled with submerged canopy flow, this is not the case actually, because the vegetation available at the bed of the channel, they prevent or they slow down the velocity profiles, which automatically prevents the occurrence of eddies at the bottom of the channel. So it's a kind of prevention of morphological changes. Well, the shear layer, which are generating the eddies, are then occurs above the submerged vegetation, which are not so dangerous for the morphological problems. On the other hand, when we have the emergent canopy flow, where the vegetation covers all the height, all the depth of the flow, then first thing that we see is that the velocity profile minimizes, it gets slower and slower, and because of the slow motion, eddies or the wakes are not so much effective. The figure is taken from the study of Tarandip et al. In 2016, and we will carry on with the other case where we are going to have some part of the channel is filled with vegetation, while other part of the channel is without vegetation. Well, the figure that we see here is depicting the plan view of the open channel. Well, right bank is with vegetation, where we can see it in gray color, this part. While the flow at the left bank moves without any vegetation to interfere the motion of the fluid. Well, as a result, what is realized here is that the velocity of the flow in the without vegetation plan is with a velocity u2, whereas where there is a vegetation, the velocity slows down and has another velocity. And of course, the water coming from the upstream side, when faces with a patch of vegetation in front of it, of course, it will be deflected towards the main channel section to move easily. Of course, this change will generate also some vortexes, but the important thing here is that because of the change in the velocity between the main channel and the vegetated part, the change in the velocities, of course, will generate in the horizontal direction the change in the pressure distribution between two sides. That pressure distribution, of course, depending on the conservation of energy principles, will apply a pressure. That pressure will be from the vegetated side towards the main channel side, where there is no vegetation, since the velocity in vegetated side is less than the main channel side. And because of this pressure, of course, the flow direction will start to generate a sinusoidal shapes, while this pressure, as it increases, will change the velocity in the upper side, because the area in which the normal flow conditions are occurring will decrease. This pressure will increase, and then the sidewise pressure will also generate it, and this will make the water to make a vortex in between the two boundaries. So this occurrence is called Kelvin-Helmholtz instability condition, and it can be seen in between two different layer flows. Well, another type of vortex that is occurring because of the patch of vegetation is von Karman vortex. And in von Karman vortex, what is happening is that if there is a patch of vegetation, of course, the flow within the vegetation will slow down, as shown in the figure, whereas the other sides where the stream is flowing, the normal flow conditions, velocity conditions will sustain. So what happens is that after the flow passes through the vegetated part, of course, after some distance of the vegetation, the U2 and U1, which are the slower motion and the faster motion, they will match after some distance, and they will force each other to make a swirl motion within the water. That swirl motion is defined by von Karman vortex, and it occurs again, creating disturbances in horizontal direction within the flow system. Well, what we think is that there might be another case, so that we should analyze how the vortexes are affecting the flow based on the stresses, and what are the effects and what kind of changes in the flow will occur in the case of canals, compound canals, where the bank of the canal is inclined and it is with rigid vegetation. This was our target aim, to understand the motion of the flow while analyzing the effect of inclined bank vegetation on flow dynamics. Well, to analyze it, we perform an experimental analysis where we did it in a 14-meter long, 1.8 meters wide glass flume, and we held it in University of Glasgow hydraulic laboratories. The vegetation was covering 5-meter long and 0.8 meters wide area at the inclined bank, whereas the running streamwise length of it was 5 meters, as I mentioned, and the sediment particles that we used during the experiments were around 2 millimeters as D50. Well, the vegetation, of course, was increased on a panel which was designed by 80 to 80 centimeters, and we performed 7 different configurations in this study. The first configuration was, of course, without any vegetation, to understand the behavior of flow without any vegetation in a bank flow. Well, after that, we performed experiments for 6 different cases. In the first configuration, as shown in this slide, we have at each 80 to 80 panels, we place at each corner 1 vegetation, and we run the flume. And then we increase by 1, and then we increase to the sides, and then to the corners again. And by this way, we increase the density of the vegetation with an order. The thing that we try to catch here was also can be labeled as the design of vegetations with linear and staggered configurations, so that the effects of linear or staggered configuration were also catched or observed during the study. We use an acoustic Doppler velocimeter, ADV, from Nortec to measure the velocity profiles in the channel at each experiment. And every time we held 10 different profiles within the channel. It is shown here as the cross sections, and 8 relative positions. So at each profile, we measure 8 relative positions just before the flow leaves the vegetated region to see how the things are changing, how within the profile velocity is changing. Well, what we observed was expected result, but it is usually omitted actually, because always the people are saying that if there is a vegetation in the channel, it's urged to minimize the velocity so that it retards the flooding conditions, etc. Unfortunately, when we don't have the velocity, when we don't have the vegetation all along the canal, but at the bank, this does not happen actually. The velocity in the channel, it starts to increase in the main channel, while it slows down in the at the bank section, in the inclined bank section. Well, the figure shows us the velocity profiles, and it is clear that when there is no vegetation, while the velocity profile is somewhere here, as we start to increase it, and when we come to configuration 5 and 6, there is a change in the velocity in the upstream, where we have the velocity profiles moving with further speed. So clearly we observe that there was a change in the velocity profile with an increasing amount. Well, in the case of the shear stress, what we measured in the experiments was that 84% increase we observe in the bed shear stress in the main channel at the close to the center line of the main channel, and 23% increase in the shear stress was observed at the toe of the inclined bank. These were observed by the experimental studies, but of course, we start to wonder what is happening in the 3 dimension after we held those experiments. So well done. The conclusions were, it is found that with increasing vegetation density, flow velocity increases at the main channel, while reducing at the riverbank. Bulk velocity at the riverbank region, it progressively decreases from the case of no or without vegetation to that of dense vegetation configurations, and it exhibits a drop of about 17%. The increase of riverbank vegetation is seen to lead to an approximate doubling of mean bed shear stress at the center line of the main channel, as well as increase of the bed roughness. Well, these are the conclusions that we obtained, but we still wonder about what is happening in 3 dimensions. So in order to observe what is happening in 3 dimension sense, we work for computational fluid dynamics model. And in this model, we use ANSYS software. It helps us too much. We use the Reynolds average Navier-Stokes equations. We use K omega turbulence models, and we developed the model with approximately taking care of aspect ratio of 1.25. Well, the smallest size of the mesh that we used was 1.5 millimeters, and for that complex geometry, the number of elements was going up to approximately 3 million elements. So we made a detailed study, and we tried to observe in 3 dimensions what was happening in the study region. Well, of course, the initial idea was to validate the computational model. So for the validation, we compare the velocity profiles that occur in the channel of computational study with the experimental results. And we make the adjustment accordingly until the error, root mean square error of the two data was ranging between 0.01 and 0.007, which means 1% to 1000%. Okay, and after we sustain that result, we are satisfied with the results. We carry on with the profiles of velocity within the main channel at the locations that we had it in the experimental studies. And what was observed was clearly seen in those figures. Well, for example, the green line is showing the flow in the first experiment where we didn't have any vegetation in the channel. And here, checking the main channel for A, B, C, D profiles, it is clearly seen that the velocity when we have an increase in the vegetation at the inclined bank, the speed of the velocity was increasing, the velocity profile was increasing within the main channel. At A, B, C, it is clearly seen. And what is happening at the same time is that as we move towards the inclined bank where the vegetation, rigid vegetation was there, first of all, the velocity profiles were decreasing, the average velocities were getting slower and slower, and when you compare it with the no vegetation, of course, they were less than the no vegetation conditions. And another thing was, as we approached to the bank, since the shallow water conditions were occurring, instead of parabolic velocity profiles, sigmoidal shape profiles were occurring in the channel. Well, in the case of shear stresses, Reynolds shear stresses in the main channel, we analyzed for different configurations, and the evidence was clear that at 2 points in the whole channel, the Reynolds shear stress was effectively increasing. One of them was, as was expected, was in the main channel. At the bottom of the main channel, the shear stress was increasing. But meanwhile, a more increase was observed in the interaction point between the vegetated point and the main channel. So the change in the velocity in the vegetated part and the main channel shows a great change in the Reynolds stresses. And because of that change, of course, we believe that we were to observe Kelvin-Helmholtz instability conditions, and how much, what was the effect of it, was the second question that we should answer. Well, to do that, we perform the velocity ratio analysis, which needs the magnitude of convection velocity, which is the average velocity for the velocity in the main channel and the velocity in the vegetated part, and the differential velocity, which is the difference between the velocities in the main channel and the and in the bank where the vegetation was there. Well, using those two, their ratios, and multiplying it by 0.5 will give us a velocity ratio of lambda. And the lambda, if it is greater than 0.3, it is the limit. If it goes above it, it means that Kelvin-Helmholtz instability conditions, the vortexes, vertical vortexes, are available in your channel. So the analyzers, computational analyzers were clearly here. You are seeing the results based on the beginning, middle, and at the end of the vegetation canal, how the velocity profiles in the plan view changes and how the KH type instability occurs in the interaction point. Well, mathematically, with the numbers, if you want to prove it, well, we have this figure, and in our figure, it is clear that as the configuration increases, the dense population starts to increase, and this dense population will end up with, as we can see here, at the beginning, since the vegetation were not so dense, were not so effective in the flow, the KH type instability were not so occurrent. But starting with C3, configuration 3, 4, 5, what we observed was our values, especially at the end point where the flow was totally passed through the vegetation, and it's after 5 meters, it starts to leave the vegetation part. What we observed was the increase of the lambda values and going up to 5, up to 6, which means that Kelvin-Helmholtz was there. This was the proof of it. Well, as a conclusion, the shear stress at the center line of the main channel tends to grow as the vegetation density at the inclined bank increase, and this increase was observed up to 90%. And another observation was that the mean flow velocity at the main channel increased by 33% as the vegetation density at an inclined bank starts to increase. Coming to C5, C6, we observe all those changes. Well, another one is that the staggered arrangement of rigid vegetation elements penetrated more than linear arrangement on the magnitude of velocity ratio, which means that the staggered distribution of the vegetation at the bank was favorable, was creating more favorable conditions for the onset of Kelvin-Helmholtz instability conditions. And this was clear in C4 and C5 configurations. That's all for me. Thank you very much for listening to me.
Thank you very much, Professor Dr. Umut TÜRKER, for the valuable and interesting presentation. It's always a pleasure to follow your research.
Thank you. Take care.
Thank you. Our second presenter in this session is Professor Chihi from Tunisia. Unfortunately, she couldn't be with us due to technical problems. However, she has shared her pre-recorded video presentation with us, and now I would like to share her video presentation with you.
Good morning. First, I would like to thank Professor Hüseyin for inviting me to this international conference, and it is a pleasure for me to be here with you. I am HAYET Chihi, professor at Center for Water Research and Technologies in Tunisia. I'm going to talk about building 3D geomodels for water resources management. I'll share my screen first. Okay. Yeah. So, building 3D geomodels for water resources management. For my talk, I'll start by introducing geomodeling, the major challenges and the tools proposed when dealing with complex aquifer system characterization. Then I'll get to and try to present some case studies on regional faulted aquifer systems and some applications for water recharge, and hydrodynamic modeling. Three-dimensional geomodeling is an efficient tool to visualize and exhibit the surface and the subsurface geological configuration of aquifer systems. It allows a wide processing opportunity to combine all related reservoir and water data, and this to better understand aquifer systems functioning in order to improve groundwater resources evaluation and enhance water management and preservation. However, geological heterogeneity at all scales combines with sparse sampling requires important consideration concerning the data type, source, quantity, quality, and distribution. Let us clarify these challenges. Reservoir systems are derived from complex geological processes, mainly deposition, erosion, diagenesis, fracturing, and folding. This leads to heterogeneities at multiple length scale that may affect the reservoir continuity. This figure or this photo illustrates clearly noticeable heterogeneity. We have various complicated geometry induced by the stratigraphic pattern and the discontinuities structures such as faults and fractures, and evidently facies and petrophysical variation. The heterogeneity may also be induced by faults that impact fluid flow patterns in the reservoir units. This is the main idea, how fault may change the connectivity and the dynamics and how it interacts with the aquifers and the compartment within aquifers. This heterogeneity that we see on the land surface is occurring in the same way in subsurface, and this leads us to the second challenge, dealing with the data sampling. Direct data such as exploration well, seismic field, geochemical data are limited to reproduce the whole reality. And that's why we are applied to are faulted and acts with aquifers and the compartment within aquifers. This heterogeneity that we see on the land surface is occurring in the same way in subsurface, and this leads us to the second challenge, dealing with the data sampling. Direct data such as exploration well, seismic field, geological, geochemical data are limited to reproduce the whole reality. And that's why we are applied to model plausible images of the reservoir systems by means of 3D geological modeling. In fact, recent advances in data integration and modeling techniques using appropriate modeling workflow with suitable software allowed reliable prediction of reservoir geometry and facies distribution, and more importantly, the lateral extent of permeability barriers, including fault surfaces and clay beds. By the development of consistent multi-source databases to cover the uneven data distribution and precisely define the parameters that are essential to describe the stratigraphic and the structural continuity. These characteristics are inferred through two variables that are the elevation and the attitude of the geological interface. Involving multidisciplinary approaches such as geological and geophysical investigations, interpolation procedures, including geostatistics and potential field methods, allow to enlarge the database by extending data from inequalities and outcropping analog data, and to make the best use of the geological reasoning to parameterize the geological concepts and properties, trying in this way to constrain data scarcity and to ensure the geological realism. Let us explain these techniques through some case studies. 3D geological modeling is actually carried out on a proper basis for 3 case studies with different objectives, as we will see later, but are based on aquifer systems characterization. The 3 aquifer systems are located in Tunisia, 2 in the north, in Tibursouk and Hamem Zriba, and the 3rd is lying in the Jfara Basin. I'll introduce briefly the 2 projects dealing with the aquifer systems in the north and gives more details about the projects dealing with the Jfara Basin aquifer systems. So the first project deals with the impact of agricultural activity on soil and groundwater quality. The second, we are called to study the impact of the mining industry on groundwater and the soil. The third, we undertaken this project to characterize the aquifer systems of the Shfara Basin. We focused our researches on developing innovative methodologies for stochastic characterization of faulted aquifer systems. The objective is to understand the functioning of these aquifers at local and regional scale. Let's see how the geological modeling was conducted. The Shfara Basin hosts several aquifer systems, as you can see here, that are faulted and interconnected. Most significant water formations are hosted within the Triassic, the Jurassic, the Cretaceous, and the Neoplio-Quaternary intervals. To achieve the aquifer systems modeling, we collected 70 seismic lines, about 400 exploration wells and boreholes, 11 geological maps, satellite images, and digital data from geological outcrops. All these data were harmonized, geo-referenced, and organized in a common geographic information system. On this base map, you can see that features such as stratigraphic interfaces, faults, and faults are commonly observed on the west side of the study area, where the sedimentary units are outcropping. These features were digitized and included in the database. Along the Shfara plain, the bedrock interfaces are completely buried under the Neoplio-Quaternary deposits. The location of the boundaries could be recognized through the geological cross-sections or seismic data. Offshore, the database was extended to study the defined sequences under the sea. All these data deliver complementary information that allow insights into the source and subsurface geometry and the spatial continuity of reservoir units. The general workflow is based on joint structural functional approaches. The first geological modeling process involves several sequential steps carefully performed, starting by the geophysical and geological investigation to map the fault network and to recognize the hydrostructural compartments. All the derived data from these steps are integrated to construct the geological model. Then dynamic data are integrated, processed, and correlated with the geological model results to study the reservoir connectivity. This allows to establish the conceptual model of the water flow path. All this constitutes a support to simulate the water within the aquifer systems and manage underground water within this system later. The modeling process begins with a definition of the stratigraphic framework at regional and local scale, taking into account the contact relationship between the units, conformable and unconformable, conformable and unconformable. This is to provide a reference for regional geological mapping in terms of stratigraphic division and lithological identification. 9 lithostratigraphic units are to be modeled. The geological investigation, geophysical investigation, we start first by the geological, to present the geophysical investigation. After picking the horizons, time structure contour maps were generated using Kriging interpolation, followed by time to depth conversion. The depth converted surface show the true position of the mapped faulted and the distinctive structures. A thorough geological investigation was carried out to understand the spatial distribution and extent of the reservoir units. After coding according to the nomenclature presented by the stratigraphic pile, boreholes and petroleum wells were used to construct numerous well-regulated geological cross-section. The topographic elevation of each cross-section was extracted from the TTM. Furthermore, some other related data noted here: extension, the fault traces, orientation, and attitude derived from the outcrop observation, the geological knowledge, and previous seismic investigation were included to improve the drawing of the configuration through the cross-sections and to better reproduce the subsurface geometry. Here is an example of a geological cross-section along southwest to northeast direction. The faulting system splits the study area into horst and graben blocks and engenders a global downtilting towards the northeast direction, with an important lateral facies and thickness variation. Here we can observe the major compartments hosting the Zeskutin Aquifer and the Jorf Aquifer that are separated by the Zarat fault. And in the Zeskutin Aquifer, we have 3 major compartments: the Dahr compartment, the southwest uplifted compartment according to the Mednin fault, and the north downshifted compartment. The figure shows here the fault network that was mapped through the seismic and geological investigation. All these faults created the compartmentalization of the aquifer systems as reproduced here in detail on this figure. Okay, here we summarize all the derived input data, including the original data, the petroleum wells and the boreholes, the interpreted seismic sections, the geological cross-section that were digitized, the analog data coming from outcrops, and the calculated data, mainly the reservoir bounding surfaces that of the reservoir units that were pegged using ISAT software. The box in the center as you can see, represents the input geological contact and orientation data points of the geological interfaces to be modeled, and also the location of the modeled section, as you can see in yellow here. These data are integrated in GeoModeler to interpolate the different bounding surfaces of the 9 stratigraphic sequences. The interpolation method or procedure is based on the potential field method and uses the geostatistical co-creation estimation, 2 main variables that are the geological contact and the orientation data. Faults are modeled through the integration of the discontinuous depth functions. After validation, the results of the 3D geological modeling are displayed in 3D visualization of the different aquifer systems, the fault system, and also we can display the modeled sections. The interpretation of these results may provide better understanding of the structural framework of the study area and the layering pattern of the regionally extended reservoir formations and their interconnection. They may also support further modeling studies, as we will see later. A regional geological interpretation of the 3D model representing the aquifer systems show that the modeling honors the data, but also reproduces the actual configuration of the study area and the distribution of the aquifer systems. In fact, in the southern domain, the Permian sedimentary unit hosting the reef reservoir, you can see it here, and it can also be seen even on the surface. Here we have the Jebel Baga de Mednin. To the east lies the Triassic sandstone aquifer. To the north, in the center here, lies the Zuscotin aquifer that is separated by the Mednin fault from the Miocene-Jorf aquifer extending along the northeast sector of the study area. On the west side, we recognize the Dar and the Merth aquifer. As a part of the results of this project, we performed a reservoir connectivity analysis to deduce the conceptual model of the water flow path on the basis of the rigid piezometric map, displaying the regional and the local flow path, the regional flow path along all the aquifer systems, and the regional local flow path direction within its compartment. So this connectivity analysis, we say that is based on this rigid map of the piezometric data, but also on the modeled cross sections that underwent a thorough correlation of the potentiometric gradient lithologic properties along the different compartments of the aquifer systems. This correlation allowed to study the hydraulic behavior of the extended faults, mainly the major ones along the north-west-southeast direction, such as the Medellin fault. We can see on these sections that regionally the groundwater is recharged in the Dahr mountains and flows towards the northeast direction to the Mediterranean Sea. At smaller scale, local recharge typically occurs from smaller mountains such as Tejra or from outcropping reservoir units along the along the west side domain of the study area. On the other hand, we can see that the major north-west-southeast faults segment the reservoir formations and appear to function as hydrodynamic features that condition the reservoir connectivity and influence the water flow path from one aquifer to another one, or from one compartment to another one within the same aquifer. This analysis was done for the different identified compartments within these aquifer. But here we present just 3 of them. The analysis helped so to construct the conceptual model of the water flow path at regional and small scale. The modeling results were also used as a base through a combined geological hydrogeological approach to map the potential groundwater recharge zones and to propose suitable type and location for MAR systems. This work was performed by Emin Mesni, a PhD student, and was presented in this conference. Moreover, the second geological model was constructed for the Shfara of Gibbs aquifer system and was used as support to perform a hydrodynamic modeling. Also, this work was presented in this conference by Mohamed Amin Hammimi, a PhD student. After this brief review of geomodeling and how to use it in the aquifer system management, I would like to underline 3 words that are understand, predict, and behave. The philosophy of geomodeling is based on these 3 words. Actually, we need to understand the reservoir properties and their distribution in order to efficiently predict the external and the internal architecture of these reservoirs in order to know how they behave. And this would allow to better understand the functioning of these aquifer systems and surely to improve the groundwater resources evaluation and management. At the end of this talk, I would like to thank all the contributors for these works, and mainly Emin Mezni. And also I would like to thank the organizing team for this valuable organization. Thank you.
Thank you very much for the valuable presentation, Professor. We couldn't host Professor Chihi directly, but many thanks to her for showing the courtesy of sending us her video presentation. Now, I would like to invite our last speaker, Dr. Oladipo from the Eastern Mediterranean University. Thank you for joining, Dr. Oladipo. Doctor, I think you're on mute. Can you please turn on your mic?
All right.
Yes, we can hear you now.
All right. Thank you for having me here. I'm an associate professor of material and environmental chemistry from Eastern Mediterranean University. Today, I will be talking on water and wastewater treatment technologies. My major focus is going to be on resource recovery from wastewater. Briefly, I will show you some of the few things I will talk on. I'll briefly go into the pollutions that everybody knows we are having big problems with right away. And we're going to look at water as a resource instead of as a problem. I will also look at some few conventional water treatment technologies and then look at how we can use it to go into wastewater-based resource recovery treatment technologies. Under these technologies, we're going to look briefly into using microhydro and electrochemical resources recovery method. And I will share with you one of our research from our own lab where we have used the electrochemical technologies to recover valuable resources from wastewater. As we all know, we are facing a lot of water pollution, and the major reason is that water, due to its unique solvent properties, it is highly vulnerable to pollutions. Several ions, polar molecules, can easily dissolve in water. And also, these days, there's growing population, industrial growth in different countries. All these combined together are generating a lot of waste. And most of these waste are being dumped into the water bodies directly. Common waste we've seen around, we've seen the heavy metals, organics, and also there are lots of emerging pollutants like hormones, enzymes that are being dumped into the water bodies. Looking at the statistic we have over here, this is obtained for 2020. The statistics shows the environmental issues that we face in the world. If we can look at it, we see that water pollution is about 25%, which is not so far from issues like global warming, and also people facing poor quality drinking water is so much high. And the main reason is because there is industrial boom. So what should we do with this? This water pollution is actually causing a lot of water shortage. In fact, according to the UNESCO, in the next few years, let's say in the next 2030, over 40% of the water it's going to be deficit. And this is going to be a big problem for the society and economic development. So we are in 2021 now. We need to start thinking, what can we do to avert these problems? Unfortunately, our need is actually increasing so much. If you take China, for example, China is a powerhouse of industry. It's growing. There's huge urbanization, industrialization, and all these are creating some sort of pressure, releasing different effluents into the water bodies. Some of these effluents are treated, some of these are not treated. Up to 80% of the China's rivers have been contaminated by organics. There are a lot of results and reports from China that shows that the rivers are highly contaminated. And if you look at the projection, this projection shows that from 2005 to 2030, China will need roughly over 500 billion cubic meters of water will be needed. And looking at the percentage, how it is distributed, 300% of that is going to go into industry. This is not surprise because there's increase in industrialization in China. Going to India, we're going to see that it's similar way around. However, the need for water in India is more into the municipal and domestic need. Coming to Europe is still very high because currently there's also some sort of industrial booms within European countries. And we can see all sorts of that. All these need for water actually generate all sorts of influence. However, we don't have the water. The water is gone. What should we do with this water? Should we treat it? Yeah, there's a lot of industry that have been treating the water. In fact, 80% of the wastewater that is produced is neither collected nor treated. Most are released into the environment without proper treatment technology. Only few of them, just 8% of industrial and municipal wastewater is treated. Although these statistics is actually different according to different economies. So when we look at high economic countries, about 70% of their wastewater is being treated. So we're talking of countries like the Northern America, Australia, and some part of Europe, actually. However, when we go into the middle income countries, these value actually decrease from 70 to 38. That is a huge decrease. Going to the low middle income countries, it falls further. So according to this chart, high economic countries, they are able to treat their water. But the water that is being treated here is majorly the industrial water. Why the domestic water? There's also some sort of differences in the treating of domestic water. Most time, we talk about water as a problem, especially the wastewater, which is actually a problem. However, we need to change the way we look at wastewater. Instead of looking at it as a problem, we may also look into the resources that are contained in this wastewater. Currently, we are faced with limited resources. The industries is growing. We need a lot of resources. Population is also growing. However, most of this wastewater is rich in several resources. So instead of just throwing the wastewater off or just using conventional treatment technology, we may look at those abundant nutrients, the chemical energy, and other promising materials that the wastewater contain. There's an image here. This image is actually very old. It's from Canada. This report comes from 2002. But why is it significant? If you look at it in 2002, 293,000 tons of agricultural runoff are being released to the surface water and the groundwater. Also from the industry, a huge amount of this goes into the surface and the groundwater. We all know that agricultural runoff mostly consists of pesticides and other chemicals that are being used. And this is going to be a valuable resources for taking in things like nitrogen, phosphorus. So if in 2002, we've got this much, when the population is quite low compared to this time, I strongly believe that this value would have increased more than 10 times. Now, most of these major wastewater is basically coming from the industry and also domestic uses. In the past, some of the wastewater treatment technology also think of recovering some valuables. Specifically in 1970, sludge from the municipal wastewater was simply disposed of. But moving forward to 1990s, these sludge are being collected in forms of biosolids, and they are useful for agricultural purposes. Some of it are converted into biofertilizers, while some of them, valuables like phosphorus, nitrogens, are being recovered from it. When we move forward to 2000, we can see that some technology have been designed to also contain bioenergy, like biogas, are being recovered from this wastewater. We know that biogas contains roughly about 70% of the methane, so those are being recovered as well. Then we move forward to 2010. Some other resources are being retrieved. So in the domestic and industrial wastewaters, what are the resources which we can actually collect? We can collect energy. So most of these water coming from domestic, municipal, and industrial contains valuable source that energy can be retrieved from. Energy in forms of hydrogen. We know that hydrogen is of less carbon it has high energy, so it's going to be a very pure source of sustainable development. We can retrieve organics, precious metals, and other chemicals. One other important nutrient is those coming from wastewater, like food industries, dairy industries. Most of the food processing industry, even restaurants, hotels, almost all the times you find the restaurants serving the clients, the customer comes in there. Most of the food are not completely eaten. They get thrown back into the sink, and this contains valuable materials. So we can actually recover nutrients, biosolids from this. Also, there are some unexploited resources that currently the research is not focusing much on them. Things like bioplastics, enzymes, and some valuable vital minerals. They can all be recovered from domestic water and industrial water. So the point is this: many of us or industries look at the wastewater. After the industrial activities, these wastewaters are merely treated and thrown off. They throw them back into the large water bodies. And we are currently facing problems with resources. So we need to think of a way to not just treat the water because we want to reclaim the water, but we need to be able to also recover valuable resources from this water. Looking at common conventional wastewater treatments, we can see that this wastewater treatment technology is actually not designed to recover valuables. The conventional wastewater treatment are commonly used in the central wastewater treatment plants. So this plant treats various sources of water. The process is basically designed to be in 4 steps. Majorly is in 3 steps, but this will also depend on the final use of the water. The first step basically is going to be the pretreatment of the water itself. So large solids, cans, plastics, they are all separated in the pretreatment stage. And this water is then sent down to the primary treatment step. So in this step, thick solids are being recovered using sedimentation technology most of times. So in this stage, you're going to have the sludge that settles down below the tank, and the oil and grease goes up of the tank. Then this water is then sent down to the secondary treatment technology. So in this part, mostly the biological components of the water have been treated. So most cases, the wastewater treatment technology stops at the secondary treatment. However, if such water will be needed for drinking purpose or for some other industrial activities that need it to be much clean, they get sent to the tertiary treatment step. So, however, most of the industry actually stop at the secondary treatment. And as soon as it's treated at the secondary stage, they get released back into the water bodies. But if we need it for drinking purpose, such water is sent air, where things like toxins, microorganisms, and some possibly heavy metals are going to be removed using more kind of advanced oxidation process, electrocoagulations, and several other technologies. But the question is this: if we look at all these parts, there's no step where those valuables are going to be recovered. Although there are some plants that have optimized the system in such a way that during the primary treatment, some of these biosolids are being collected. However, when you look at industrial water, like water coming from dairy industries, it contains a lot of things. It has the biosolids, proteins, oil, fat, and many other things that may not be treated at the primary treatment step. So we need to look into other kind of technology that we can incorporate into the conventional treatment technology so that we can actually recover these valuables from the wastewater. So even if this wastewater is being treated with this technology, as I've mentioned, it does not mean that we have saved water, because they get treated, and those water that is treated, sometimes just a simple technology is used and the water is being released. But if you go to the industry these days, the industries will prefer to take their water from the fresh water sources. They take it from the ground, they could take it from the surface, rather than reuse the treated water. So if the industry are focused on taking the water from the freshwater resources, these resources will get actually depleted, especially considering the fact that it is not so quick for fresh water to actually be replenished. And if we keep taking from it, we're going to exhaust all the freshwater resources. Therefore, we need to consider other treatment technology that is not just treating the water for the purpose of throwing them back into the water bodies, but also a treatment technology that is quite sustainable. So, but what does it mean for wastewater treatment process to be sustainable? How can we actually improve upon the conventional treatment technology? Because this system is already designed, and then we're talking about recovering valuables from this water. So how should we improve on it? The first point is this: we need to think about what is sustainable. In order to actually upgrade the conventional water treatment technology to recover valuables, first and foremost, we need to know what is sustainability. If sustainability is known, then we can actually focus on designing a more sustainable system that is not just sustainable, that is also eco-efficient and energy efficient system. This way, we can recover the resources, we can also reclaim the water. So, sustainability is actually defined as a process of maintaining change in a balanced environment. So, if we're going to exploit resources and we're going to use any technology, we need to use them in such a way that there's a balance within the whole system. And that will be of benefit for the human needs and also the society and the environment totally. I would like to go into some of those technology that can actually recover valuables from wastewater. We've got a lot of technology actually that are being used currently to actually remove these valuables. And one of the low-cost technology is using microalgae to remove these valuables from wastewaters. So the microalgae, they are quite important. They are kind of a system that most small-scale industry and medium-scale industry that are commonly releasing this water can easily use. So wastewaters that are typically rich in nutrients will require microalgae cultivation so we can recover a lot of things, nutrients. For instance, industry like olive oil industry. So we look at olive oil, it produces a lot of wastewaters. And when you look at the countries that are producing olive oil, like Cyprus, Turkey, and other related countries, you find that most of those producers, they are small scales. They cannot afford to set up an expensive technology. Mostly, they recover the water after the processing of the olive oil, and those water have been thrown back, or mostly they use evaporation ponds to just evaporate the water. But if we look at olive oil wastewater, it's a very valuable source of resources because it contains a lot of phenolics. So these phenolics can be used in a lot of industries, cosmetic industry, pharmaceutical industry. So if a producer that is producing olive oil can make use of technology like microalgae, which is very easy to use, then such resources can actually be recovered. What can we recover? Using microalgae, we can recover nitrogen, phosphorus. Most of these can be converted into fertilizers. Another valuable things that we need to look into is the advantage of using this technology. It's actually energy efficient. It can recover a lot, high nutrient removal efficiency. Also, it's a source of higher biomass production. It releases low emissions. So this is an appropriate technology. One other very valuable advantage is that this technology can easily be integrated into the conventional water treatment technology. So when you have a water treatment technology that is traditional, basically we don't really need to spend a lot of money to actually integrate this kind of technology so that we can recover the values. Even though it has its own advantages, it does have its own disadvantages as well. Because this microalgae, there's going to be a lot of research to see how the community of this microalgae can actually recover valuables. The other technology that is very valuable these days is electrochemical technologies. So this is actually important. Recently, although this technology has been existing for long, however, there is increasing interest on this particular technology. Why? Because it's actually high in efficiency. It's very easy to maintain. In fact, the construction of most of the electrochemical technologies is quite very easy, not so expensive, and they can be automated. And the good thing about it is we can recover many things, not just materials recovery, we can also recover energy from it. So for instance, when you look at wastewater coming from dairy, as I mentioned before, using electrochemical technologies, we may be able to recover the nutrients, which is the phosphorus, the nitrogen, and some other things. Those could be converted into biofertilizers. And also, because of the fact that electrochemical technology produce gas like hydrogen in the cathodic compartment of the system, we can actually recover hydrogen as well. And this hydrogen can be used to power the system again, or it can actually be recovered and then used for some other things. This electrochemical technology is actually splitted into different types, and each one of them does different things. So this is the way it looks like, an electrochemical system. So we've got a compartment. One of it is the anodic compartment, and the other part of it is the cathodic compartment. So various designs can actually be made. In fact, it doesn't really need much. The major things that these needs is just the electrodes. That is the major things. So there are a lot of different electrodes that people are using these days, be it iron, aluminum, zinc, and so on and so forth. And the power source. This system can actually be powered in two ways. It can be powered using direct method or alternating current. So different research is going on both technologies. The good thing about it is using electrochemical technology, variable things can be recovered. We can recover heavy metals, hydrogen, sulfur, and many other things. In fact, we can recover some unexpected resources, which we can also add values to them. So, in a very short description of the system, this can be modified into whatever we want. So we've got our wastewater somewhere there, and the reaction happens in these anodic parts. In the cathodic parts, hydrogen gas is generally being produced. So when hydrogen gas is produced, that hydrogen gas mostly it does two things. It can help in the flotations of unsettled sludge, because this system will produce the sludge, and those sludge can contain those valuables, and also the hydrogen gas can actually be tapped. So this is a very good technology. In this case, which is my final note, I'm going to just show you one, which is a case study from our own lab. So what we try to do in this particular research is to look at a way to produce hydrogen gas. Almost all the countries are interested in hydrogen. There's a lot of research currently on hydrogen. But when you look at it, hydrogen is generally produced, in most cases, from water. So when you split the water, we're going to have hydrogen and oxygen. So why do we want to split the water? Because we said the water is actually in deficit. We need the water. So why using the water that is limited? So in our research here, we look at something that's it's going to be much better to recover hydrogen, not just to recover hydrogen, to also recover sulfur, which is highly useful in a lot of industry. So what do we think? We think of toxic gas like hydrogen sulfide. So hydrogen sulfide is generally produced from different industry. Think of coal gasification, petroleum industry, and also you can also get hydrogen gas from various natural processes like volcanic eruptions. So in this part, we collected water that is actually contain this toxic gas. First, one of our motivation is this. We need water, so we don't want to make use of the water again. The second motivation is the fact that to split the water into hydrogen gas, we need a lot of energy. In fact, you will need about 236 kilojoule per mole on average to split the water. Why? Because of the bonding between the hydrogen and the oxygen. It has both the polar bonds and this hydrogen bonding. But when you look at these hydrogen sulfide, we don't have hydrogen bond. So it is much easier to split these. In fact, you will need just about 20 kilojoule. So the difference is huge. 236 kilojoule to split water, and we need 20 kilojoule to just split this. So we use an electrochemical technology. But this system that we use here is not just splitting and obtaining hydrogen and getting sulfur. It also powers itself. So it has two components. The first component of this uses solar system. So the solar system starts the electro-oxidation process, whereby this hydrogen and the sulfur is being splitted. And the other component, the hydrogen that is produced, is channeled back into the system to continuously powering it. One very valuable thing we obtain from this result is we were able to obtain sulfur that is not impure. We actually obtain sulfur that is quite pure. After the characterization, we see that using this technology, most of the toxic waste containing things like these can actually lead to resources recovery. So thank you for my presentation, and I would like to just hammer it once more. Water, especially the wastewater, we should not see it as a problem. We should see it more as a source of resources. So wastewater should be something we want to sell because it contains rich, valuable things, nutrients, metals, and other valuable things we can recover from it. Not only that, if we recover these valuables, we can also have our water. So the process that is being proposed in this presentation is a method that we can integrate resource recovery with a conventional water treatment technology. Most of the water treatment technology we have, like advanced oxidation process, these are very good. They can treat all sorts of wastewater. However, we cannot just recover the resources. For instance, when we look at industries like hospitals, pharmaceutical industries, valuable antibiotics are being released into the water streams. Most of the antibiotics that we consume, just about 3 or 4% is actually absorbed into the body system. Others goes into the water. Even though the concentration in those water is tiny, if the bacteria or any other pathogen comes in contact with these, it's going to develop into super robust bacteria, leading into what we call antimicrobial resistance. But these water from hospitals, from pharmaceutical industries, cosmetic industries, all these can actually be collected, and the valuables, those pharmaceuticals, can actually be recovered, purified, and also reused. It can be reused for animal feed and some other things. Thank you for this presentation. I would like to end my presentation here today.
Thank you very much for your presentation, Dr. Oladipo. It was an
Thank you so
interesting research. Also, thank you very much to all professors who have contributed and honored us in this session. Professors, I would like to ask you, is there anything you would like to add?
For me, I don't have anything to add, but I welcome any questions regarding to this technology anyway.
Okay, it looks like we don't have any questions at the moment, but surely if we have any questions, I'm sure the audience can find you. You provided your email address as well, all of our professors.
All right. Thank you once again.
Okay, thank you very much to everyone. I would like to announce that this is the end of the second session, and the next session will begin at 2 o'clock in the afternoon. Thank you very much for being with us. Goodbye.
Catching a bus, never